All right, chemistry. Let's start your second half video lecture for Chapter 7, Section 1, talking about formulas. Yesterday we introduced the system for naming for binary ionic compounds when the metal is located in the main groups. In this lecture we will introduce the stock system for nomenclature, which is used when the it's still for a binary ionic compound, but when the metal is one of the transition metals, aka the D block elements, that form multiple charges. So let's get started. Some metallic elements, and again, they're all found in the D block. Not every single D block element, but all of these elements are in the D block. Form some metallic elements that form cations. For example, chromium, cobalt, copper, iron, lead, manganese, mercury, nickel, and tin can form cations of more than one charge. Sometimes they're a positive 1, sometimes they're a positive 2, sometimes they're a positive 3, sometimes they're a positive 4. The only thing I want to point out is they're never negative. Okay, they're always still positives, they're cations, but the charges, the magnitude of the charges will vary. For these cations that have multiple ionic charges, we simply place a Roman numeral in parentheses that is equal to the ionic charge after the name of the metal. Why do we have to do that? To indicate what the charge is, otherwise we would have no way of knowing. Note, when we use a main group metal, we do have a way of knowing what the charge is. We simply look at the main group number. But with these elements, for example, copper and iron are very common examples to use in these types of problems. There's a type of copper that has a +1 charge. We call it copper 1. Copper with a +2 charge, we call it copper 2. There is an iron that has a +2 charge, we call it iron 2. There is an iron that has a +3 charge, we call it iron 3. Now, when we go to use the stock system, we follow a pretty intuitive list of procedures. First, we need the formula for the ionic compound. We need the formula. Now, because when looking at the formula, we don't know the charge of the anion. For example, in these two compounds right here, we don't know the charge just by looking at the formulas. We don't know the charge of the copper intuitively. So what we have to do, in number 2, we have to use the charge of the anion to determine the charge of the cation. Why does this work? Because this chlorine, this nonmetal, is in a main group. Therefore, it never varies in the charge that it forms. Chlorine, when it ionizes to chloride, will always be a -1. This formula tells me that there is 1 copper balancing out the charge of the 1 chloride. Because chloride is always a -1, that means copper here must be a +1. Copper 1 chloride. In this formula, there are 2 chlorides. If there are 2 chlorides, because each chloride is a -1, there are 2 of them, there's a total of -2. And in order to balance out those -2, there must be a +2. And there's only 1 metal here producing that +2, so this copper must be a +2 charge, copper 2 chloride. Let's practice some. So the first 3 practices I have here, I simply give you the types of ions that are going to make the ionic compound, and I want you to give me the formula. Then I want you to give me the name. For the last 4, I give you the formula. I just want you to give me the name. Go ahead and press pause and try these on your own. Please press pause now. All right, let's see how we did. Copper 2 and bromide. Copper 2 bromide. Iron 3 and oxide combined to form iron 3 oxide. Lead 4 and a chloride, they combine to form lead 4 chloride. CuO is going to be copper 2 oxide. CO, cobalt, right? That's not carbon, it's cobalt. And fluorine, or fluoride I should say, going to form copper 3 fluoride. Tin and iodide are going to be tin 4 iodide. And then iron and sulfur, this one's going to be iron 2 sulfide. Moving on, we're going to cover polyatomic ions. It's exactly what the name suggests. It's an ion that has several atoms. The only thing I want you to remember is that the bonds within the polyatomic ion are covalent. Okay, the atoms within the polyatomic ion are covalently bonded, but the group has a charge like an ion, so it, as a unit, is going to be involved in an ionic bond. I want you to be aware of a type of polyatomic ion. And again, everything you need to know about this type of polyatomic ion is present in the name, oxyanion. Now, I hope you see very clearly the last half of that word is anion. That means it's negatively charged. It's a negatively charged polyatomic ion. The first part of that word, I hope you see, is oxy. It refers to oxygen, meaning this polyatomic ion has oxygen in it. So just by looking at the name, we know that an oxyanion is a negatively charged polyatomic ion that contains oxygen. And that's going to be useful when we get into naming acids. So please remember that. Now, when we start to name ionic compounds that contain polyatomic ions, we use the exact same naming system. The writing and naming systems are the same for ionic compounds with polyatomic ions. However, if more than one polyatomic ion is needed in the formula, okay, in order to balance the charge, remember that's the goal, we have to balance the charge. If we need more than one polyatomic ion to do that, like sometimes you need more than one oxide to balance whatever the cation is, the formula of the polyatomic ion is placed in parentheses and a subscript is used outside the parentheses to show how many of the polyatomic ions are needed. For example, iron 2 nitrate. Nitrate is a polyatomic ion with the formula NO3. To balance out an iron 2, 2 nitrates are required because a nitrate polyatomic ion has a charge of -1. So I need 2 of them. To indicate that there are 2, I simply add a subscript 2, but I need these parentheses around the nitrate. Realize if these parentheses were not there and I typed FeNO3 it would look like iron, nitrogen, oxygen 32, as though there were 32 oxygens, and that is simply incorrect. So we need those parentheses around the polyatomic ion to indicate it operating as a unit. Now we are done with ionic compounds. Let's move on to molecular compounds. Now remember, a molecule, when I say molecule, we're implying that it is covalently bonded, that there are covalent bonds, which means the 2 atoms, the 2 elements that are being bonded are non-metals. They're non-metals. So you call it a molecule when you see 2 non-metals bonding. And when you see 2 nonmetals bonding, you use the naming system we're about to go over, which is known as the prefix system. Now remember, hydrogen, even though it's in main group 1, it is still a nonmetal. The other thing I want to warn you about is because we're talking about molecules which are covalently bonded, we are not going to be concerned with balancing ionic charges. The ratio of elements is not determined by their ionic charges like when we were doing ionic compounds. We would make sure that the charge is balanced. That's not the case here because we're not forming ions. We're covalently bonded, so we're not balancing charges because there are no charges. Now, pretty simple, straightforward system with the numerical prefixes. First, we write the name of the first element in the formula. We write the name of the second element in the formula, but we use the suffix IDE, very similar to how you do in an ionic compound. Then we use numerical prefixes to show the number of atoms of each element present. For example, P2O5. The first element listed is phosphorus, so I write down phosphorus first. Second element listed is oxygen, so I write down oxygen first. Then I go back and I add numerical prefixes, and here they are if you're not familiar with them. Because there are 2 phosphorus atoms, I add a di in front of phosphorus. And because there are 5 oxides, I add penta in front of oxide. So I get diphosphorus pentoxide. Here's a couple run-throughs. So we see P4O10. I add a tetra in front of the phosphorus, a dec in front of the oxide for tetraphosphorus decoxide. For CO, I have carbon, and I have an oxide. I have 1 oxide, so I add a mono in front of the oxide, and then carbon dioxide. Sorry, I add a di in front of the oxide to indicate that there are two of them. So I say carbon dioxide. In terms of the element that is listed first, you might ask, how do I know which element to list first? You list the element first that has the smaller group number, basically the element that's further to the left. Now, that element that's further to the left, the one that you list first, you only give it a prefix if it contributes more than one atom to the molecule. Notice if we go back, I did not write monocarbon monoxide, monocarbon dioxide, because the first element listed only contributes one element, so we simply don't include the mono. I hope you don't get thrown by that. Now remember, the second element is named by combining the prefix of the number of atoms, right? Mono, di, tri, tetra, on and on. And the name of the element with the root of that name, with an ending IDE. Now typically, this isn't going to be a big test question, but typically we drop the O or the A at the end of a prefix if the following word begins with a vowel, like oxide. Now, when we go to write formulas from names, right, because so far we've given you a formula and you've written the name, but if I give you a name and ask for a formula, this is what you do. You write the formula for the first element in that compound name. So down here it's carbon dioxide. The first element is carbon, so I write down a C. Second element is an O, so I write down, second element is oxide, so I write down an O. Then lastly, I add subscripts to each atom, indicating the number of atoms present according to the numerical prefix in the name. All right, guys, let's try some practices. Go ahead and press pause and see how we do. All right, guys. First up, sulfur trioxide. Second up, iodine trichloride. Next up, phosphorus pentabromide. Now we're trying to write formulas from names. CI4, PCl3 into O3. All right, guys, so far in this lecture, we've gone over the stock system for nomenclature, which is naming ionic compounds that have metals that form multiple charges, as well as the prefix system for naming molecular compounds. We will pick up acids next time we meet. All right, guys, I will see you next period.